We will start now.
Okay.
Good morning, everyone in Chile. Good afternoon, all of you here in the UK. Welcome to the new session of the online meetings of the Worldwide Energy Network Distinguished Lectures Program of the Solar Energy Research Center, SERC. Today, we have invited Professor Surojit Sen from the University of Nottingham in the UK to talk about the World Solar Challenge and how to make solar cars practical. Surojit is a PhD in electrical and electronic engineering and specializes in multidisciplinary systems involving electrical, electronics, mechanical, and thermal. His main research interest lies in electrification of automotive systems in a sustainable manner, including areas of high energy storage systems, high power motors and motor drives, and overall system optimization in vehicles towards minimizing carbon footprint from well to wheel. Professor Surojit Sen, thank you very much for accepting our invitation to this initiative. Now, the screen and the microphones are yours.
Thank you very much, Marco. I will start with sharing my screen quickly. Brilliant. Could one of you confirm if you can see my screen?
Yes.
Brilliant. Okay. So, hi all. I'm Surojit. I'm an assistant professor in electromechanical engineering in the University of Nottingham. Today, I would be talking about the World Solar Challenge, and from there, how we are building a car and how we are exploring ways to make solar cars practical in the future. Right, a bit of introduction about myself. Thank you, Marco, for introducing me. A quick introduction, this one. So 2013, I did my bachelor's in engineering in instrumentation and control. 2017, I did an MSc in automotive engineering from Nottingham University. 2022, I finished my PhD. I was just earlier this year in hardware and loop, technology for electric vehicle motor drives. And right now, as I said, I'm an assistant professor in electromechanical engineering. My research interests lie in automotive design and motorsport. I've always been about cars, and that's what I'm doing at the moment. Recently, I have moved on to sustainable and electrified powertrains as well. And I've been working on with the students and the faculty in Formula Student Racing. It's the car that you see in the bottom right, and the Solar Challenge project that started about 1.5 to 2 years ago. Okay, so agenda for today's meeting is split into 3 parts. So first, I'm going to talk about the World Solar Challenge. Next, I'm going to look at 2 teams who produce the top cars and are usually consistently the winners of the World Solar Challenge and other regional solar challenges like the European Solar Challenge. And lastly, I would talk about how to design a practical solar car. So the third part of the agenda would be the key area that I'd like to focus on. And I'd like to think that I'm going into a bit more detail on that. Okay, so let's start with the first topic. So the World Solar Challenge. I've got a QR code for you to scan. If you want to visit the website, you'll find more details on there. So what is the World Solar Challenge? So the World Solar Challenge is an event that happens once every 2 years, and it's planned to happen in 2023 in October. As you can see in the map, it happens in Australia, so the whole of Australia, basically. It's a 3,000 kilometer drive, which happens over 4 to 6 days. Starts in Darwin, which is in the northern part of the continent, and ends in Adelaide, which is the southern part of the continent. And all the competing cars are asked to drive along that route, as you can see over there. There are various checkpoints in the middle, and all all cars need to arrive at the checkpoint within a stipulated time frame. In the 2019 challenge, there were 47 teams split over 3 classes, and there were about 200 volunteers. So it is a fairly big competition. Okay, so let's look a bit more into the classes of the competition. So first off is the Challenger class, which is designed to be the cutting edge in technology, the state of the art. So the plan is to design a single-seater solar car, really small footprint, small, sleek, and designed to be really fast. The goal is to get across Australia in the quickest time possible without stopping for recharging the battery pack. The next class is the Cruiser class, which is the aim is to make an efficient, effective, and a practical solar car. So the key term here is practical. So you need to have 2 or more seats in the car, ideally 4, and the goal is to get across Australia efficiently and effectively. In the Cruiser class, you can stop twice in the drive of 3,000 kilometers to charge your battery pack. You've got a limited number of hours that you can charge. So it's all about strategizing. The last is the Adventure class, which is non-competitive. And usually the older teams, they bring their older cars for demonstration of capability. Sorry, I think there was a bit of a distraction over there. Thank you, Alex. Okay, so these are the 3 main classes, and we are planning to enter our first solar car from University of Nottingham in the Cruiser class in 2023 October, which is next year. So why should we follow the World Solar Challenge? There were several reasons, some of which I have noted down here. So it's a showcase for new technology and innovation. So currently the best cars in the world that make efficient use of solar technology enter this competition. So it's not just a student project, it is actually one of the biggest events where the best that the world can offer in terms of solar technology for transportation is presented in this competition. So many people, there's a lot of coverage, a lot of PR for this event. And also it's a really good competition for students who want to enter the area of sustainability when they graduate. Many big companies recruit students right away attending this competition. All right, so that was about the World Solar Challenge. I'm going to quickly spend a few minutes looking at the top 2 teams as I see it. So the first one is the University of Eindhoven, which is in Netherlands. So they have been doing the Cruiser class for so many years now, and they are by far, in my eyes, they're the best teams. So they're really pushing the envelope in terms of producing cars which are actually very, very practical. So I've shown 4 cars over here, and they have the most interesting one is the Vita, the one you see on the top left. It is actually a motorhome. You can sleep in there. You can take a shower in there, and the solar panel on the top, it basically comes out and expands. So it's a really practical vehicle. Again, I won't bore you with details. You can very much have a look at the website. There's a QR code if you want to scan that. So Eindhoven, in the previous slide, that was a Cruiser class competitor. Now this one is University of Twente, which is again in Netherlands. They really specialize in the Challenger class competition. So this is the single-seater, not practical, but at the cutting edge of the technology. These cars do that entire, apologies for that. These cars do the entire 3,000 kilometers with no charging stop. So they start at the start track with a full battery, and they are driving the entire distance purely on solar car. So again, there are quite a few cars they have been building over the last few years. Recently, other teams have also entered this arena. Most notably is the Sonnenwagen Aachen team, which is in Aachen, Germany. They recently came first and second in the European Solar Challenge. Okay, so how to design a practical solar car. Now, this is the most interesting bit of my presentation, I think. We've set the context about what the competition is, why we want to follow that competition, why we want to build a car for that competition, and which are the top teams, so the teams that we really should be aiming for. So now, let's look at how we actually design a practical solar car. Okay, so it really is a step-by-step process. It's not rocket science. If you just follow a simple set of steps, anyone can build a solar car. It's not that difficult. So the design process happens over a period of 12 months. That is how we do in the University of Nottingham. So we spend the first 12 months designing a good car, and the next 12 months, it's a 2-year cycle. The next 12 months is focused on manufacturing and testing the vehicle. Okay, so first milestone is requirements capture and define the KPIs. The KPI stands for key performance indicators. That's milestone number 1. We should be aiming to finish that in the first month of the project, so 1 out of 12 months. Next milestone is choosing the favorite layout. So after defining the KPIs, we want to explore different layouts of the vehicle. So where the seats go, where the passengers go, where the battery goes, what's the wheelbase of the car, where do we put the wheels, for example. And that's once it's an iterative process, so different vehicle layouts and trying out different aerodynamics of those layouts. There's a bit of a back and forth in that process, but by the 3rd month of this 12-month project, you want to get to milestone number 2, which is choosing a favorite layout, the one that gives that offers the most promise. Next step is actually starting to design the car. So first step in the 3rd milestone is to break down into multiple systems. So obviously it has to be different systems. So for example, the chassis, the powertrain, the bodywork, the electrical systems, they are all separate subsystems. So this is at this stage, after 3 months of the project, the team really wants to split into different subsystems of the vehicle. Each subsystem then goes through a design and validation process. Thank you, Abdullah, for muting. So design and validation is an iterative process, as I said. Different subsystems are designing and validating based on different metrics. After that process, a preliminary system is ready. So that's milestone number 3. So you want to spend about 3 more months on this. So you are now 6 months into the project. Last step is milestone 4, where you bring together all of these subsystems, throw them together in a common CAD and do a system level validation. So this is really the second half of the project. So you want to spend about 6 months going back and forth between different subsystems and bringing together all of the subsystems together, testing them in software, and then producing a well-designed car. So milestone 1, 2, 3, 4, that takes about 12 months. And if you've done all the processes correctly, spoken with each other, you would have a well-designed car in 12 months. Last 2 milestones are milestone 5 and 6, where you actually manufacture and test the car. This would usually happen in year number 2, where you want to spend the first 6 months manufacturing the car and then latter 6 months testing the car. So hopefully that all makes sense. And we will now go into a bit more detail in milestone 1 and 2. Right. So as I said, milestones 1 and 2 should be finished ideally in about 3 months of the project. So that takes about a quarter of the project duration. It is very important to spend some good amount of time talking to people, try to set some targets that are realistic and ambitious together. So it's finding the exact balance between realistic and ambitious. So that's very important. it's very easy to start off with one particular concept, which you have not explored. So it's very important to have many competing concepts, explore all the ideas possible, and start with from a position of informed decision. Okay, so step one, requirements capture. We start with a free body diagram, as you can see in the top corner. It is nothing but elementary school physics. So it's just Newton's laws of motion that are used to estimate how much energy is required to push the car through the air at a desired speed. Okay, so this is again affected by various things like aerodynamic properties, weight of the car, how much friction is offered in the wheels, what is the efficiency of the entire electric powertrain, and so on and so forth. This is also affected by the slope of the terrain on which it is climbing or going down. So you need to really find out the elevation data of the route map as well. It's very simple to find that information. You can simply go onto Google Maps and find it out. So you can see on the bottom that I've done a route, and you can clearly see how the elevation data is. So the first half, as it makes very perfect sense, the first half is climbing into the land, and then it's a descent. From this, you want to extrapolate the energy consumption for the battery, because at the end of the day, the whole project is just about making an efficient car. So how do you make a car efficient? You need to make sure that you are consuming the least amount of energy from the battery to push the car in the wind. Okay, so once you've set up a model like this, hopefully you should have something that looks like this. So on the top, you can see the vehicle model, which gives a rough estimate of how much energy is needed to drive in each stint of the travel. So you can see I've split that into 3 stints. So at each stint, you get to charge once. So at Tennant Creek, for example, you charge once. And again, you can stop at Coober Pedy and you can charge for the second time. So this is a very simplistic model based on Microsoft Excel. Many teams do it in a much more complicated way, but as a starting step, you really don't need to go complex. As I said, it's all Newton's law of physics, and it's just school maths, really. So as you can see on the far right, I have estimated the total energy that's consumed from the battery. Next one is the sensitivity analysis. That's the second most important part of this whole exercise. So the sensitivity analysis tells you which metric, like speed, friction, affects the energy consumption the most. At the end of the day, the objective is to minimize the energy consumption. So you want to really know what metric of the car should I change so that I'm consuming less energy. So that's what sensitivity analysis does. So again, in that same Excel, I've done a quick drop-down menu where you can select which metric you want to change, go +10%, -10%, and see how much the battery consumption is increasing or decreasing. Okay, so what we have found based on these analyses is that optimizing aerodynamics is the most important bit, which makes sense because you want to drive efficiently at a decent amount of speed, so you're not driving really slow. Some of you might know aerodynamics is directly proportional to the square of the velocity. So the aerodynamic drag increases with the square of the velocity. So as you go faster, as the car is driving faster, maximum amount of energy from the battery is consumed to cut through the wind, basically. So from all of that step, what you want to arrive at is to define a set of key performance indicators or KPI targets. So these are the KPI targets that we have set within the team. Coefficient of drag, front cross-sectional area, total weight we have aimed to set below 650 kilos. The average speed we need to drive the car at is 75 kilometers an hour. Battery energy consumption, battery energy capacity that we need to make the trips. total maximum weight of the cells, wheelbase and turning radius are again two of the important things which you want to set, because you want the car to be driving in a public highway. So you want the car to turn in a desired amount of turning circle. So that's the first milestone, and you want to finish all of this in the first month of the project. You also want to rank them. So you've got a fair number of KPI targets that you want to achieve, and you will find out once you start doing the project that they are all competing targets. So if you want to really reduce the battery energy, you may see that the wheelbase is increasing. So you want to rank all of them in a particular order of priority. So in our case, as we said, we want to give the highest rank to the aerodynamics properties, then comes weight, then comes the wheelbase and the turning circle radius. Okay. Now, step 3, vehicle layout concepts. So this is going, once you've finished your first milestone, setting the KPI targets, this is when you want to choose the vehicle layout concepts. So as you can see, we have produced several vehicle concepts. 6 have been visualized over here. So different layout concepts have different properties. So in this one, we've got a 1-to-1 seating style with a battery in the back. This one has got a battery in the front. This one has got battery in the central tunnel. So obviously that means that the entire wheelbase is shorter, but the width of the car is larger because you have to fit the battery pack in the middle. And similarly, there are other concepts that have been shown over here. So it's very important to explore all the options, because you never know which one is going to come out as the best concept. So you really, at this stage, you want to keep all your options open and see which vehicle is the best. Next step, we want to wrap all of these vehicle concepts in a hypothetical bodywork package. So as we said, aerodynamic properties optimization is the most important at this stage. So we want to ensure that all the bodywork packages are very close to identical to each other, so you can get relatively close and accurate numbers. So now you take all of this bodywork package and do a CFD simulation on it. So CFD stands for computational fluid dynamics. You can check how much air resistance this vehicle would offer when a wind of 75 kilometers per hour is flowing towards it from the front. So at the end, once you've done all of that, you want to really find out what the frontal area and the coefficient of drag values are. So for the 6 concepts we found out, we've got a few favorites. So concept 1 and concept number 4 offer the least amount of aerodynamic drag. So we can now say that with a bit more confidence, okay, concept number 4 is the one we should be going for. It is very important to keep in mind that these numbers are not going to be accurate in real life, because simulation never gives you realistic numbers. What it does offer is a relative impression of which concept is better of the other 5. So it's all relative, it's not accurate at the moment. Right, step number 5, choosing a favorite concept. So that's milestone number 2. This step took 2 more months, so now you are in month 3 of the project. So the things to look out for is, as I said, do not blindly believe the numbers thrown by the simulation software. They are almost always, they're never accurate without doing any benchmark testing. This is, up until this stage, it's all a group effort. So all of the different subsystem groups, they need to work together in this project. It's very important to have a very good and open line of communication between the different engineering departments. You also need to talk to experienced people. The things that experience offers is unparalleled. You really want to talk to people who have done this before. Lastly, think about the stuff that you can buy off the shelf. So building your own thing every time is not the best idea. So few questions that you want to ask when choosing which concept is the best, which has the best aerodynamic properties. Simple solution is also very important. You, as a first car, you want to build a really simple design. Which one's least costly, which one is the lightest, which one has the most amount of solar irradiance on it, and so on and so forth. Right. So hopefully all of that has made sense so far. So now we are going towards milestone number 3. So this is where we can now that we've chosen a favorite concept, at this stage, we can break the group down into individual subsystems and work in a bit more islanded fashion. So different groups can work on their bit of the car on their own independently. So as you can see, systems have been broken down. They all go through an iterative process between design and validation. So again, you start with design and you validate it for various metrics. Don't worry, we'll talk about what the validation steps and design steps are for each subsystem in the next few slides. Once you've done that, what you want to arrive at is come up with a preliminary system. So once all the subsystems are designed and partially validated, you bring them all together, and that's milestone number 3. So you want to spend about another 3 months getting to milestone number 3. So all of this should take 3 more months, and now you're at month number 6 of you. So you're halfway there. So one thing I'd like to clarify over here, so with our solar car project, we are currently in milestone number 2. So we have chosen a favorite layout, but we are in the process of going through the later stages. So just a quick clarification, all the screenshots and pictures that you see now on is going to be for our Formula student car. So that is a project that we have been working on for the last several years, about 5 years now. But at the end of the day, a car is a car. The KPIs are different, but the design and validation process is simple and it's very similar. Right, break out into subsystems. So there are 3 main subsystems in mechanical discipline. So chassis, suspension, and aerodynamic and bodywork package. Electromechanical, it's an electric car, so we have to look at the electrical aspect of it. Battery pack and other containers for the electrical components fall under the electromechanical subdivision. Electrical and electronics is purely, doesn't have much interference from the mechanical engineers. And we are looking at hardware and wiring, electronics and PCB. So PCB stands for printed circuit board, and the software aspect of it. So these are broadly the 8 subsystems or subgroups that the team is split into. These are the engineering teams. Of course, no team is complete without the non-engineering, the non-technical aspects. So we have to look at the support teams as well. So support teams in the University of Nottingham, we've got a business development team, a public relations and marketing team, a procurement team. Obviously, you want to buy things, just designing something is not going to help you. And the management and HR team, where the different teams, all the members are managed and tasks set. Okay, so we would only be talking in this presentation, we'd be talking about the technical aspects. But again, we cannot forget about the support and the non-technical teams, which are absolutely crucial. Right, step number 7 and 8, design and validation. This is for the mechanical engineering groups. So as you can see in the pictures, we've got a chassis, which is nothing but the structure of the car, which holds everything together in place. At the end of the day, if you think about a chassis, it's just a big bracket to hold everything in place. You've got the suspension. It's the bits which connect the wheels to the chassis, and the aerodynamics package, which is the 3rd subsystem in the mechanical engineering. So the way you start designing this is you start always, you start with the tires, start with the wheels. You start with the wheels, so suspension teams define what geometry they think would be best for a car. From there, you start working on the powertrain, which we'll talk about in a bit. The battery boxes are defined, and then finally the chassis group tries to create a space frame structure to hold everything together. Last step is the aerodynamics, which is defining a bodywork which is going to offer the least amount of resistance when cutting through the air. Okay, so in terms of validation, the bits in red are the validation aspects. FEA, or finite element analysis. In software, you can check how much stresses and how much deformation happens when you load the structure in various ways. So for example, in the chassis, when the car hits a bump, or when the car brakes hard, or when the car is actually involved in a crash, you want to ensure that the chassis doesn't just break apart, fall apart, and crumble under those stresses. So you ideally like to stress the chassis in 3 to 5G in regular operation and up to 20G in crash scenarios, and see that it still retains its shape. The primary objective is to make sure that the driver is very safe, the driver and the passengers are safe, and also the powertrain aspects. So for example, the battery pack doesn't get crumbled when there's a crash, because that can cause a fire, which nobody wants. The other validation that we do is CFD, which is computational fluid dynamics. That is used to study how aerodynamic it is. So you can simulate using software to see what the cross-sectional area is, what the coefficient of drag is, and all that. Okay, so that's the mechanical groups. Now we come to the electromechanical groups. As you can see, I think this is the most tricky part of the project, because first of all, it's electro and mechanical. So this is multidisciplinary. Both the electrical team and the mechanical team, they are very tightly intertwined in the design and validation process. So there needs to be a really good tunnel of dialogue between the two teams. So the bits that are covered in this area are the battery pack. So you design the battery pack, but you start off from the battery module that you can see. So this is from the student, as I said, we are designing with cylindrical cells. So you start off with the design process of the segments, then you have multiple segments in the battery pack. And at the end of the day, you want to come up with a design which can take various stresses. So again, you do FEA on the battery pack, and you want to stress it at least 10 to 20G stress conditions to ensure that the battery doesn't crumble upon when there's a crash situation and there isn't a fire. You also want to cool the battery packs. That's another important thing. So you are doing CFD on the battery pack as well. So you can see that there are fans over here, which pushes air through the cells to cool them down. So how do you define how fast the fans need to be running at? So again, all of that comes from the CFD analyses, and we find out, okay, the fan needs to push air at a certain speed to keep the temperatures of the cells below a certain warning level. Distribution box is another container which falls under the remit of electromechanical teams. Okay, lastly, electrical and electronics. This is where all the electrical electronics students or team members, they come together and define the various electronic packages. So for example, in the pedals, the accelerator pedal has got sensors on it. So defining the sensors comes under them. Printed circuit boards or PCBs. So all of the custom electronics are designed and assembled and manufactured by the electrical and electronics team. This also includes the electrical logic. So you can see this logic diagram is a quick snapshot of how the solar car battery pack looks like. It's a logic diagram. All the lines are basically wires. And lastly, software. So software is the brain of the car. You need to tell the car how to behave upon different conditions. In terms of validation, so all the PCB circuits are simulated in software like PSpice. Software is again something which takes 90% of the time to develop software is done with validation. It only takes 10% of the time to actually write the lines of code. So debugging and testing with the hardware is often which is the most important and critical part of software. Right. Step 9, preliminary systems are ready. So that's milestone number 3. By now, if your team has followed all the processes correctly, you are halfway into the project. So you've got all of the subsystems partly designed, partly tested, and at this step, about halfway in the project, you really want to bring all of the subsystems together in CAD and repeat the design and validation iterative process, but at a system level. So do not get fooled by the detail of the CAD pictures at this stage. So clearly these pictures are after everything has been done. So at this stage, you would not be seeing such level of detail. So you can see the vehicle assembly on the top left, the powertrain, so the drivetrain of the Formula Student car that we have, which is the motor, is this bit and attached to a gearbox and then attached to the wheels on this end. And this is the entire powertrain package, the battery pack, the low voltage 12-volt battery, the vehicle control unit. So that's the brain of the car. You've got 2 motor drives and the distribution box on this end. Okay. Now, milestone number 4. As I said, this is the last bit, but it's the most time-consuming bit and the place where all the teams really scratch their heads trying to get everything together. At this stage, all the subgroups that had split out and have been working independently, they are now coming together and they have competing interests. So every subgroup is saying, oh no, my thing is more important. The other one says, no, my thing is more important. So at this stage, you really want to manage expectations for all of the subsystems and just make sure that the key performance indicators that you've defined in milestone 1 are you continually revisit that step and make sure all the groups are working together effectively. Okay. System validation, we've got mechanical and electrical electronics. In mechanical engineering, you want to make sure that all of the designs, all of the CAD works are now fleshed out in more detail. So you want to start putting together the nuts and bolts in the CAD, in the drawing. You want to make sure, so you also want to look at the small bracketries that need to be defined. You want to, another really important thing which often gets missed is it all assembled? Can you assemble all of this in a proper way? So can you reach these nuts and bolts with a spanner once everything's in place? So that's also a key thing to look at. In electrical electronics, you want to do system simulation. You want to test the hardware. So you can see in this picture, we are testing the motor corner unit in a dyno. So just making sure that the motor drives in an expected manner. So this also lets you test the software as well. Right, step number 11, final design approval. This is milestone number 4. This is the end, in theory, this is the end of the design process. So you spent another 6 months putting everything together and you've got a well-designed car in theory. So at this stage, you want to look at product availability. So all of the things that you need to buy, all of the consumables, all the metal sheets, all the metal tubes, tires, all the wheels, all the nuts and bolts, all the cables. Do you have all of that available? You, at this stage, now that you've got a very well-defined car, you're also looking at the total weight of the car. Have you met your expectations? Have you met your KPIs? Total cost of the car as well, and total carbon. That's also a very important thing in modern world. You want to make sure that you've got a reasonable amount of carbon that has been put in the process of putting the car together. You end up with a final bill of materials, and that's when the procurement department takes over and starts buying things to put together. Right, okay, so that's step 11. That's the final step of the design process. We've got manufacturing, year number 2. As you can see, we've got some pictures. That's the solar car, our first generation solar car, the Renault Twizy, which is in the process of production. That's our Formula Tune car, which is again in pieces at the moment. These are some pictures from last year. We are about a few months before the event, and you can see everything is being built together. So many people are working towards building this. This is the old car. The new car is being built for Formula Tune over here. Testing, that's again the later half of year number 2. Very important step in the process. You want to test the car. As you can see in Formula Tune, it's an electric car, so we do a rain test as well. So we sprinkle water from different directions for a full 2 minutes and ensure that the car doesn't catch fire, basically. We do some driving tests as well, and we do a tilt test as well. As you can see, we tilt the car up to a 60-degree angle and make sure that the car doesn't fall over. So hopefully, if everything has gone as per plan, you're now in month number 24. So that's the end of the 2-year design process. You would have a car which has been designed very well in the first year, built and tested appropriately in the second year. Right, so that's the end of my presentation. Hopefully that made some sense to you at the very least. If there are any questions, do feel free to ask. I've put together our social media handles down here and our website on the left. If you want to use your QR code scanner on your phones, do follow us and ask questions if you want. Thank you very much for listening.
Thank you very much, Surojit, for your presentation. Very interesting topic. A lot of fun as well.
It is a lot of fun.
So
yeah.
Congratulations for that.
Thank you.
Now we have some time for some questions, but I would like to give the microphone and the control of this space to Professor Rodrigo Palma from University of Chile. Rodrigo.
Yes, Surojit, thank you very much. Very interesting, your presentation, and virtual welcome to Chile. It will be great that we keep in touch. I am some interesting questions. We have already a question from Shriha in the chat. I will look to that. Only previously to say that we are very engaged as country in this type of challenges. In 2007 was the first participation of Chile in the World Solar Challenge in Australia with our Aeolian, and after that some teams from Chile returned to Australia. So there is, we are a solar country, and this type of challenges are very interesting for our students. So I hope some of the attendees will ask some questions. But I start with the question from Shriha. In step 8, electrical system design, you mentioned that 90% of the software development time goes to testing, but hardware won't be ready at this stage. What can the team do to support debugging in realistic conditions to iron out issues as early as possible? So
that's a good question. Thank you, Shrija, and thank you, Rodrigo, Professor Palma, for the introduction of University of Chile and welcoming me to present this in this webinar. Thank you very much. So coming back to the question, if I understand correctly, you've asked what are the steps we can ensure to make sure that we iron out the issues well in advance. So I think there are two things to look at here. We need to think about the fact that a lot of the software can be actually debugged in software itself, so without coming to hardware. There are software simulations which are often used by the software engineers, but also the fact that a lot of that cannot be done without a physical hardware. So at this stage, I know we said we're not doing any production in first year, but the electrical electronics team actually end up producing a lot of prototypes in hardware as well. So the PCBs often in the first year, in the design year, a lot of PCBs are actually produced and manufactured just specifically to aid in the debugging process.
Very interesting. So if there is some reaction, any other question from the group? Can you repeat, because I arrived a little bit, some minutes late, but only to clarify. Now you have an active team in Nottingham working on this issue and you are expecting to be in 2023 in the next World Solar Challenge?
We are, yes. So we are, the team has, so we are the University of Nottingham racing team. So we work on the Formula Student for quite a few years now, but we did start the Solar Challenge project about 1.5 to 2 years ago. We have been building a vehicle and we do want to attend the Solar Challenge in 2023. But again, there are some open-ended questions whether we would be able to secure the funding, because traveling to the other side of the world is very expensive, as we've realized. So it's still not a complete yes, but we are in the process of managing the budgets.
Great. This is the same situation in our team. It's very challenging. We receive the support from the faculty, but only they achieve at least one industrial partner with some level of support, and the team is working hard to put. We will go with the 4-seat approach.
We are also going with a 4-seat approach for the second generation design, but in the first generation, the one the picture that you saw in here, that's the first generation car. So we wanted to start with a Renault Twizy, which is a road going car. So that's the first generation car. We've heavily modified the chassis and the suspension, and we are planning to retrofit as a solar car with a big roof on it with the solar panels. And we plan to take that car once it's finished building and testing over to Australia, if we are able to go.
Great, incredible. I'm happy that the leader of the Chilean team in University of Chile, Alejandra Holguín, is a lady. This is also very interesting for us to move the things here in Chile. How did you deal? And perhaps, Alejandra, if you want to make the question directly, you can take the microphone. But how did you deal with the pandemic? What was the most difficult thing?
Yeah, that's, I guess, a question that every team has had to face. Thank you for the question. The way we dealt with pandemic was, so purely from solar car point of view, we didn't start until the pandemic was almost on the decline. So we started the project in 2021. We did face the brunt of the pandemic during our 2020 Formula Student build year. So the way we dealt with it was we kept number of people inside the workshop to a minimum level. So unless anyone is particularly required to attend in the build phase, we didn't let them come. And we did go over to a lot of remote studies in the design phase. So as it turns out, we really do not need to be facing each other physically to design a vehicle. So the entire first year of the project, which is the design phase, can be done remotely. And that is one of the good things, that one of the blessings of the pandemic, that we got to realize, or well, people around the world realize that a lot of things can be done remotely.
Fully agree that this is also, I'm happy if you can make some bridges with the teams, and Alejandra, you have the contact. But for Perdana and Ibrahim Irfan, we have some additional questions. Would you give information about the specification of the car, like solar size, load, power, voltage, I know this is special for each category in the race. So it's part of what we can see in the homepage from the Solar Challenge. But if you want to add something additional, please.
I think different, as you said, different categories have got different requirements. So for the cruiser class, the requirement is, again, it depends on the particular solar cell technology that you're using as well. So for our case, we've got a total 5 meters square of maximum solar cell coverage that we can use. Challenger class vehicles have got different requirements. Some have 6 meters square, depending on the solar panel, depending on the PV panel technology, and some have 4 meters square as well. In terms of looking at what sort of weights are we should be aiming for, as we said, for our second generation car that we are designing at the moment, which would come after the Twizy car, we are aiming to build a car which would be less than 650 kilos, but that is by no way what the competition is. As I said, the best teams, the best cruiser class teams, for example, Eindhoven, they build cars which are about 400 kilos. The lightweighting is one of the most important things in building a solar car, and efficient and effective use of carbon fiber comes in hand when you start doing that. But again, carbon fiber is a very, very expensive part of the project. It's very expensive. It's not repairable. So my suggestion to new teams is you should only go for carbon fiber once you've built 2 or 3 steel space frame projects.
Great. And the final question from Ibrahim is, when working on a project of such a large scale, setbacks often come in unexpected circumstances. Has your team come across any such setbacks through your progress along the project? And if so, how have you overcome them?
That's an interesting question. Thank you, Ibrahim, for that. So I think, pandemic is obviously one of the big setbacks that everyone in the world saw a few years ago. But more recently, with the Australia travel, as I said, finding the budget is the latest challenge that I'm facing as the project manager of this project. So that's the only one that comes to mind. And the way we are trying to tackle that is we've got a fantastic PR department. We are finding out, so the department is actively looking for various sponsorship and grant applications in the world, be it industry or be it academia. So we are applying for several grants, and often we found that it's usually maybe 20% of the applications that we send out actually comes back with a positive response. So it's one of those things where patience is key, and do not lose hope is the key thing in here. Keep applying and keep there is light at the end of the tunnel.
Okay, I think yes, Marco, please, I give you back to the word, and so you can make the final remarks. Thank you very much, and we keep in touch, Surojit.
Thank you, Professor Palmer.
We are almost finishing this session, and I would like to finish your presentation and your talk with a question, probably some step ahead. What do you think if the current technology is efficient enough to make solar cars available for commercial use? If not, what do you think are the trends and challenges we have as an engineer right now?
Right. So I think that's a very good question. It's got profound consequences. Thank you, Marco, for that question. And I think at this stage, development of the technology in PV is the most critical bit. So even today, the most advanced solar panels, they can only give up to 25 to some really expensive solar panels give up to 35% efficiency. So you're still only able to use a quarter of the total sun energy that you're getting back. So the first thing as engineers is we need to really open up our minds and explore different materials, different technologies, and try to push that number higher up, go up to 45, 50%. And I'd like to like pull an analogy with internal combustion engines. So internal combustion engines, petrol, diesel, they also have an efficiency of about 30, 35%. But over the last few decades, that number has been pushed up to almost up to about 50%. So it's definitely possible. Trying to get that number higher up. But in the meantime, I would think making sure that the vehicle development process keeps that bit in mind. So if you start by simply retrofitting a normal traditional car with solar panels, you will never come to a good solution. So it's very important to start the vehicle design process from scratch and develop a solar car purely to develop a solar car, not retrofit an old car, traditional car into a solar car.
Okay. I'm probably, in my personal opinion, I'm not expert in solar cars, but probably it's not only related to increase the solar panel efficiency, but probably energy storage capability is something we have to focus as well. Okay.
Definitely, yeah.
What do you think? Yeah. Okay. Thank you very much for your time, Surojit, and all the attendees of this talk. It was very, very nice presentation, very interesting topic. It's very nice to see the lab. When you see a lab like the picture you have, you notice that there are people working there. So it's
yeah, it's not the neatest.
Congratulations for the work.
Yeah, thank you very much. Thank you, Marco.
Yeah. Okay, thank you very much, everyone. And the next presentation will be on November 22nd. We will send the invitation to everyone. And for this session, we have invited Professor Fred Ladger from Aalborg University. Okay, thank you very much and keep in touch. Bye-bye.
Thank you. Bye.
Bye-bye.